Hi and welcome everyone. This is Pavan with Dremio. We're here to go ahead and close out track number 2 for the Iceberg Summit with Zhang from Xiaomi presenting leveraging Apache Iceberg to build Xiaomi's unified Lakehouse platform. Just a quick reminder, if you guys do have any questions, we are going to get to them towards the end of the presentation. So please use Ask the Presenter tab on the right-hand side to ask any questions you may have, and then we'll go and get to them towards the end. And with that, please join me in welcoming Zhang. The floor is yours.
Okay. Hi, everyone. My name is Yujiang Zhong. I'm so honored to join today's Iceberg Summit. So let me introduce myself a bit. I am a software engineer on the big data computing team at Xiaomi. Here we build the Lakehouse infrastructure to support various internal use cases across the company. And today I will be sharing how we build a Lakehouse using Iceberg. Okay, let's get started. Let me first introduce our company and the usage of Iceberg here. So Xiaomi is a technology company focused on the full ecosystem of human, car, and home, providing users with smartphones, electrical vehicles, IoT devices, and internet service. So we use Iceberg as our data warehouse in many use cases. And today we have over 100 PB of data stored in Iceberg. And Iceberg has become the first choice for our data warehouse storage. Here is the agenda for today. So this presentation will be in 3 parts. First, I will provide some background on our previous data platform and the challenges we faced. Second, I'll explain how we leveraged Iceberg to address these issues and build a unified lakehouse. And finally, there will be some summary and future outlook. So let's start with some background. So previously, our data warehouse was mainly built on the Hive and Hadoop ecosystem. So we use multiple compute engines for different workloads. For example, we use Flink streaming for real-time data processing, and we use Spark for batch processing, and Trino and Doris to support OLAP workloads. And as you can see, our compute pipelines were fragmented because Hive doesn't integrate well with stream processing, and the streaming pipelines typically run on message queues like Kafka. However, since message queues are not directly queryable, the data needed to be synced into Hive tables for querying. And another issue is that the query performance of Hive is limited. So if users need a better performance, they'll have to load data into the Doris data warehouse for ad hoc queries. And we had a separate data warehouse dedicated to private data, which we call it a private cluster. So our old data warehouse based on Hive has some issues. The different compute pipelines were separated, such as streaming and batch, because Hive is not really designed for stream processing, and Hive is full of pitfalls, like the lack of ACID support and poor schema evolution. And addressing these issues consumes a lot of time for data engineers. And another issue is that the entire storage was based on the Hadoop HDFS, since Hive is not suitable for cloud object storage. So we started looking for other solutions, which is Apache Iceberg. So hi Pawan, can you help me advance to the next page? Okay. So why did we choose Iceberg? This requires explaining our vision. As we mentioned before, we use several compute engines for different workloads. We don't want to build a storage for every compute engine. So of course, we hope the storage layer has a good engine ecosystem. And in the storage layer, we hope to gradually evolve towards cloud-native storage, which is typically more cost-effective and offers better scalability. And another thing is that we want the data warehouse to be easy to use and maintain. And Iceberg is a cloud-native open table format. Its metadata filtering makes queries fast, and it also supports ACID schema evolution and many other great features. So I think Iceberg perfectly meets the needs of a modern data warehouse storage, which aligns with our goal. And another thing is that Iceberg has an active and consistently evolving open source community, which is very important and valuable to us because our data platform relies on many open source components, as you can see. So I think Iceberg really does a great job in terms of open source. Okay, the second part is how we are leveraging Iceberg to build a unified lakehouse. So this is the data architecture after we adopting Iceberg. So Iceberg offers good integration with both stream processing and batch processing. You can easily append data using Flink streaming with intervals or at the minute level. And under the guarantee of ACID, users can concurrently update tables without worrying about data correctness. And we use data encryption to protect sensitive data, makes the data warehouse more secure, so Iceberg can support various workloads. But we also run into some problems. So as you may know, Iceberg tables require regular maintenance, such as snapshot expiring, often data cleaning, and this maintenance task is kind of complicated for table owners. Another thing is that table optimization work can be really challenging, such as rewriting manifests, clustering data to improve data skipping, and reduce storage volume. So maintaining these tasks for each table would be really time-consuming for table owners. So we did some work to automate these maintenance tasks. We will collect table scan events and data statistics to find the proper columns for data clustering, and we will automatically schedule optimization tasks, including snapshot expiring and data clustering and compaction based on the table commit events. So with the automatic optimization service, users only need to focus on their data processing tasks, which is really great. But there's also a disadvantage of automatizations. Data compaction tasks may conflict with users' data update tasks. This is difficult to control because the timing of data updates is not fixed, so there might be conflicts. So currently, we allow users to turn off automatic data compaction tasks to avoid conflicts. We also use Iceberg to build a hybrid storage lakehouse. So we use both on-premise HDFS and cloud vendor object storage at the same time. So previously, Hive is difficult to use with object storage because it requires rename and list max semantics, which are not supported on the object storage, and it also lacks data compaction to handle with small files. And when using Hive, we used a strategy called HDFS tiering to move data to cloud to reduce HDFS capacity issues. But this approach is a kind of complex and is inherently tied to HDFS. But with Iceberg, data is totally decoupled from the data warehouse path, which means that the data of one table can be stored on different storage systems. And Iceberg's snapshot design and atomic swaps allows our migration tasks to not affect regular data reading tasks. So based on Iceberg, we can combine on-premise HDFS and cloud object storage to use. So here is a typical use case. This is a time-partitioned Iceberg table. The newly written data in recent days is stored on HDFS, and when the data is no longer fresh, we schedule data migration tasks to move the old data to cloud object storage. So this allows us to use both the high network speed of our self-built IDC and the low cost of cloud storage at the same time. Another use case is that we use Iceberg to protect sensitive data. So at Xiaomi, we value data security, including users' PII data and our own business data. So we use data encryption to protect important data. And different columns in the same table may have different data access restrictions, which requires us to apply fine-grained encryption. So we implemented column-level data encryption based on the Iceberg and the Apache modular encryption. So Iceberg OSS Iceberg has already defined a good encryption specification, and Apache also supports column-level encryption. We just extended the column-level encryption capabilities on top of this. So one point to note when implementing this is that in Iceberg, there are not only data files, but also position deletes and equality deletes. So different columns can be configured with different keys, but a separate key must be used for position deletes because querying any column requires reading position deletes. And the columns in equality deletes need to use the same key as the columns in the data file. So besides this, there's a key management service for key access control. So based on Iceberg, we implemented column-level encryption, which can support different levels of access restrictions for different use cases. And Iceberg makes it very easy to adopt it with different engines, ensuring data security across various workloads like streaming, ETL, and OLAP. And another thing we are working on is building a metadata management service based on the Gravitino REST catalog. We currently use the Hive catalog, but it has several issues. For example, the performance of is limited because of Hive lock mechanism, and the maintenance is kind of difficult because it is based on the client-side commits. So if there is a problem with the client that needs to be fixed, all clients are needed to be updated. This is kind of difficult because every Iceberg connector has a Hive catalog client, and Hive lacks capabilities such as auditing and governance. So we had to build the capabilities ourselves. So we're starting migrate from the Hive catalog to the REST catalog. And the advantage of the REST catalog is really attractive. So we use Apache Gravitino as the implementation of our REST catalog server. So let me provide a simple overview of Gravitino at first. Gravitino is a technical catalog for Iceberg REST spec server implementation. So you can access it based on the open API defined in the Iceberg REST spec. And by using a REST catalog, you can move the commit logic from the client side to the server side. This makes client maintenance much simpler. And Gravitino is also a federated catalog for data and AI access. It can also manage non-tabular data like pure fields, and it provides capabilities such as auditing and data governance. Here is a REST catalog architecture. So as you can see, clients can use the REST API for commit and table access. The REST catalog can really well expand the ecosystem. For example, before, we had to build another service for non-engine use cases. because not all applications can use the Swift protocol used by Hive catalog, but with a REST catalog, every application can access it based on the REST API. And in addition, the complexity of catalog operation and maintenance will be reduced because the commit logic is transferred to the server side, and there is rarely a need to upgrade the REST client. And Gravitino also provides capabilities such as auditing, which is very attractive to us. So with Gravitino, we really have the opportunity to build a unified metadata layer. With the increased catalog capabilities, we can also reduce maintenance work. I think this is just because this architecture is more reasonable. So finally, here is the summary and outlook for today's presentation. So this is an overview of our Lakehouse built on Iceberg. Our Iceberg-based Lakehouse already has over 100 PB of data, and Iceberg has become the first choice of our users. I think nowadays, very few users choose Hive tables now, which is really a good sign. And here is the outlook. As mentioned before, we hope to migrate our catalog system to REST catalog to enhance catalog capabilities. And we are very interested in the Python ecosystem because many AI data requirements are based on Python. And of course, we also want to help users migrate the existing Hive tables to Iceberg. So that's all for today. Thanks everyone for listening.
All right. Thank you so much for that, Zhang. Gonna open it up now, and please, if you have any questions, please input them into this chat on the right-hand side by where it says Ask a Presenter. We're gonna give it about 30 seconds or so here to see if anything does come up, so just hang tight with me, Zhang. Any questions? Okay. Well, I just want to go ahead and say thank you so much for joining us, Shang. As a reminder, all the sessions will be available for on demand a little bit later today. And up next, we have our final session of the event, which is going to be the replay of our closing panel that happened yesterday in person in San Francisco. So please stay tuned to go ahead and check that out. In the meanwhile, Shang, saying thank you so much for your time. And thank you to everybody as well for joining us.
So, okay, thanks everyone, and thank you, Paiwan. Bye.